Good morning, my dear student. So today I will cover one of the very important aspects of surface chemistry, or you can call it is a micellar chemistry, and that is properties of surfactant. You all know that surfactant organize, of course self-organize, and form micelles, and there are various physicochemical properties. Out of many physicochemical properties, one of the most important and characteristic properties of micelles or surfactant is critical micelle concentration, or it is sometimes known as abbreviated form the CMC. So in this short presentation, I will try to discuss some of the important aspects of critical micelle concentration, and I will give more emphasis on methods of determination of critical micelle concentration. And in addition to that, I will also discuss the other properties, because one of the most important properties of surfactant is degree of counter-ion binding, or sometimes degree of counter-ion dissociation, which is related to critical micelle concentration. And another property is called the aggregation number. And definitely, I think you all know that CMC depends upon various factors. So that is a very important question for the examination point of view. So I will also discuss some of the important factors, like if you add some electrolytes, if you change the medium, if you increase the temperature, if you increase the pressure, so what would be the possible effect? That is the topic of my lecture. Why it is not working? Yes. Now, this is the starting point, and you all are aware of these things, that, and always remember that this is a dynamic process. Dynamic process means it is a very fast process, and this small n is the number of monomers, and this m is the micelle formation. So we want to calculate that narrow concentration where that surfactant is converted into the micelles. That is one important point. Second important point, that how many monomer self aggregates and form a micelle. That is called the aggregation number. And because you know that this structure was determined by the McBain, but the model was developed by G.S. Hartley. So therefore we call it is a Hartley model, and this is available in all the books, all the research papers and other things. But what is important, why I am showing this diagram to you, that you know that if I am talking about one cationic type of micelle, so there are two important parts. As because it is cationic, So you know that this head group, this is head group, this is head group, this is head group, this is head group, and another part is their tail group, that is there. And there must be some electrostatic repulsion between these two head groups. It is quite natural. If I add some electrolytes, so that will sit in between this two head group and the strand layer. So that naturally that will affect this micellization process. Second point, what I am going to tell you, that part is very important. That is the counter ion. So in this diagram, you have seen that this is not the exact picture. Here all the counter ions, which is negatively charged, are sitting in the strand layer. So it is a perfect type of micelle. That means all the counter ions are bound, but that is not the picture. So we have to calculate the actual number of counter ions bound, as well as there is a possibility there must be some scattered counter ions are also there. That is called the unbound type of the counter ion. So that is very important to calculate the bound, and it is related to the micelle formation. That is, so first point is that I must know the actual concentration. This is the first point. Then number of counter ions, degree of dissociation you can calculate. You can calculate counter ion bonding also if you calculate one thing. So 1 minus alpha, that can be calculated with beta. So there are so many factors. Now you can understand the things. Hydrophobicity, hydrophilicity, all are responsible for this type of things. Then number, suppose there are 60, so that is called the aggregation number. So this is properties number 1, properties number 2, properties number 3. Then quite natural, you can ask me, sir, what is the shape and size of the micelle? Sometimes I call it a nano particle like that, because you know that, yes, we have in our department also now we have a instrument, that is DLS, dynamic laser scattering, and zeta sizer. So now it is possible to calculate the actual number of the size, hydrodynamic, and so size and shape, size we can measure by DLS, and also some very small potential is also developed, so that is also possible. So today I will discuss all such type of things. Fortunately, there are a large number of methods are available, and today I will discuss only very common method. Most of the scientists are using those common methods, but you will be happy to know that nowadays people are using the NMR method. People are using the surface enhanced Raman spectroscopy method. People are using the small Newton and SN SANS, small angle Newton analysis like that. So why we study all such type of physicochemical properties? Because that is directly related to their applications. So therefore, whenever you do such type of research in the area of micellar chemistry, you can take it. So we have to determine all these physicochemical properties, and you must know what are the different physicochemical properties. I have mentioned some of the here, like critical micelle concentration. One point is very important, that is called the Kraft point. When we increase the temperature, what would be the possible solubility of that surfactant? A particular point, particular temperature, that Kraft point is equal to CMC. Then one point is for non-ionic surfactant. There is a phase transition, that is called the cloud point. Then aggregation number, degree of counter and binding, I have already told you, packing parameters, aggregation number. So these are some important properties of the micelles. If there is a short question, we ask that what are the various properties of the surfactant of the micelle. So you can write that CMC is one property, Kraft point is one property, cloud point is one property, aggregation number, packing parameters, counter and binding, all these things. Then, now as I told you that CMC is the most important point. And if you ask me, sir, what is the simple definition of the critical micelle concentration? So I will tell you that it is the minimum concentration or this narrow range of concentration when surfactant self-organize and form the micelles. Now my second point, that what are the various methods? So the critical micelle concentration is the concentration of a surfactant above which aggregates of the surfactant molecule. Just you can see surfactant and micelle. So we have to calculate that narrow concentrations. And because you all know that when you just add some water in a surfactant, so the surfactant molecule get absorbed on that air water surface, and definitely gradually when you increase the concentration of the surfactant, so the whole surface will be covered by that of that surfactant, and so naturally that will also affect the interfacial tension as well as the surface energy, interfacial energy. There are so many other things. So therefore it reflects everything. So CMC is the most important property. And my student Mr. Lovekesh has prepared this PPT for me, and you will be amazed to see that there are a large number of methods are available. It is not necessary for the M.Sc student to learn all the methods, but you should know that what are the different types of the methods. And again I am happy to inform you that in your M.Sc classes or in B.Sc classes, a student used to use a stalagnometer for determination of the surface tension. The cost is, I think, ₹50. But in our department, we have a automatic surface tensiometer, and its cost is more than 8 lakhs. We purchased from our DST fist fund, and it is available in my laboratory. In my lab, you can see this instrument, the automatic surface tensiometer. That is very easily we can determine the surface tension. And before that, we also using this type of India made, indigenous. It is Japanese made, and it is indigenous GenCon type of the surface tensiometer, by which you can also determine, and by simple conductometer you can determine the CMC. So therefore I have written the first method, which is very simple and common, is the electrochemical measurement. Even we can use the potentiometer also, but I am just mention here the conductometric method, which is so simple method. Then most of the scientists and the students, they are using the surface tension method. So because we can use the contact angle measurement and other things. And there are a large number of spectroscopic methods are also available, and we do in our department all type of method. My students are also doing, and most common method is the fluorescence method. We use, I think, pyrene as a probe, and then we mix that our surfactant with that. Fluorescence intensity can be measured. So it is a very common method. And why this method is important? Because with this method we can also calculate the aggregation number. Then absorbance method, UV visible spectrophotometric method. So what we do, we take a dye and interact with this surfactants, so that is also very good. In addition to that, I will show some of the graph related to the NMR and surface enhanced Raman spectroscopy method. And the common point is that what we are doing, we are measuring any physical properties. If we are talking about the conductometric method, what we are doing, we will measure the observed conductance or specific conductance or equivalent conductance with respect to concentration of surfactant. If we are using surface tension method, we will measure the surface tension with respect to the concentration of surfactant. If we are using NMR method, we will measure the simple chemical shift and different types of surfactant concentration, like that. Light scattering method is also important. Then isothermal calorimetry method, direct we can calculate this. Then chromatography method, ultrasonic velocity method. So I have used only some methods, but today we will concentrate only on, for the examination point of view or for the M.Sc student, you must know the details of the conductometric method and surface tension method. If possible, you can learn also the fluorescence method as well as the UV visible spectrophotometric method. But you should know some, I will use some of the research papers. So this is the determination of very most common methods. Now, as you know that okay, no problem. Factors affect the CMC. Now, here okay, suppose you are using different types of hydrophilic group. Say for example, you are using cetyl trimethyl ammonium bromide, CTAB. Then you just change the surfactant cetyl triphenyl phosphonium bromide. That means you are changing the head group. So when you check or when you determine the CMC, there will be a change. Similarly, that means hydrophilic group also affects the CMC. The reason I will tell you. Then similarly, nature of the hydrophobic chain. Suppose you are using cetyl trimethyl ammonium bromide C16, then you are using tetradecyl C14, then dodecyl C12, you will be surprised to know that there is a tremendous change. Say for example, if the CMC of CTAB is approximately suppose 1 millimole, 1 or 0.9 millimole, if you take the dodecyl trimethyl ammonium bromide, it is 16, and if you take the decyl, it is 65, and that means that hydrophobic interaction plays a very significant role which affects your CMC. Then of course counter ion also plays a very significant role, because you know that if I take the chloride ion, cetyl trimethyl ammonium chloride, size is different, bromide ion size is different, iodide ion size is different, hydration number is different. Naturally that will also affect the CMC. If you take lithium dodecyl sulfate, if you take sodium dodecyl sulfate, again lithium is different, sodium is different, so definitely that will also affect the CMC. Then temperature is a very important point, and the result is very new type. That means suppose if you increase the temperature up to certain extent, the CMC decreases, but Okay, for higher temperature, in sometimes CMC increases. So there is no definite trends available for the effect of temperature, electrolyte, solvents and pressure. Now this is a very common, as I told you, that it is also I am taken from the literature, and my student has prepared this thing, that it is a very common diagram and very popular diagram, because you know that you are just variation of physical properties with surfactant concentration. I will not say that CMC is the method dependent. There must be a very close correlation between all these methods. But there are some mathematical approach, that is called the first derivative and second derivative, in order to get the correct values of the CMC. Now, you know that in conductometric method, if I increase the concentration of surfactant, sometimes what happened, the observed conductance may be increased. Whereas in surface tension method, which is also a property, when you increase the concentration of surfactant, the surface tension may be decreased. Similarly, you know, osmotic pressure, you see, like different. Similarly, chemical shift method may be different. So this is a pictorial representation which indicates that variation of physical properties, and there must be some intersection point, because one is surfactant, another is the micelle. So there must be some point, break point. So that break point is critical micelle concentration. So this is a very important research paper I have taken from a very important journal of American Chemical Society, and that is called the Langmuir. This is not my paper, but I have just for sake of knowledge, I am taking this diagram from this very important paper, and you have seen the title, surfactant self-assembly and critical micelle concentration, one approach fits all. You just go on. Now see, this is the conductometric. They are used some of the mathematics. This is first derivative, second derivative type of things. So you see here, this is the break point. Densitometry is different. Ultrasound spectroscopy is different. And fluorescence spectroscopy, we generally measure the fluorescence intensity. So the objective of showing this research paper is that one approach fits all. That means almost results will be same. Now again, this is a very common diagram, and just you can understand this very easily, that of course this is surface tension method, and everybody is aware of the surface tension of water is 70 millinewton per meter or 70 dyne per centimeter, like that. And you are just, this is two surface, air and water, there is no surfactant, pure water, and you measured the surface tension, it's around 70. It is again a pictorial representation, and then you just go on adding the increase the concentration of surfactants, so all the surfactant gets absorbed on that interfacial layer as per as the hydrophobicity and hydrophilicity, you know these things. And again you increase the concentration, and this surface is clear here, but surface is gradually covered, and when there is no space, then it will form such type of micelles, and that point is called the critical micelle concentration. Very simple diagram. It is available in all the books, all the. Again I am showing you another very good research paper of some scientists And again, it is a very modern method for us because we don't have this instrument, and this is surface enhanced Raman spectroscopy. And with the help of this, I'll show you the data. It is published in the Journal of Raman Spectroscopy, and you see that nothing, it's very simple. Here what we are taking the simple observed conductance, millisiemens, and we change the concentration. So as I told you that CTAB is just this is observed conductance is increasing, and after a certain time this is changed. And whereas breakpoint is same, but what they are doing, they are using the surface enhanced Raman spectroscopy. They are measuring the intensity. That unit is there, and you see there. So whatever the method, the most important thing is whether it is observed conductance or surface enhanced intensity, but breakpoint is same. So this is one method. Also, same their methods. Again, that is the fluorescence method, as well as they also monitor the intensity of this method. So that is fluorescence intensity, determination of the CMC of the CTV by fluorescence probing, and plot of the surface enhanced Raman spectroscopy intensity of the vibration at particular 284 centimeter and a function of CTV concentration. And in other side they are using the fluorescence intensity. These are very advanced method. If you have the instruments, so you can determine all such type of method. Now this is very simple method, as I told you that, and I think during your M.Sc first semester you have already determined the conductivity method as well as the surface tension method. You also measured the Gibbs adsorption isotherm methods and other things. So as we increase the surface surfactant, so this break point is with the CMC. Similarly, this point, sometimes because all the surfactants form the micelles, so there is no change, because there is no change in interfacial tension or surface energy, because whole surface is covered by the surfactant and there is already form of the micelles. So, but somewhere in some cases, because conductivity depends upon the mobility of the ions. So in normal cases, when the surfactant concentration is low, so the movement will be high, but once they form the aggregates, the movement will be slow, and the mobility and the speed of the ions, so there must be some constant value. Now this is also one of the important research techniques, and you have seen that they are all using different types of cationic or the anionic surfactant, that is nuclear magnetic resonance method, NMR methods, and they monitor the CMC. Now I am coming to the next point, that is called the degree of counter and dissociation. Please look it very carefully, that basically, although there are other methods available for the degree of dissociation and degree of counter and binding, but conductometric method is the most simplest method for the determination of this degree of counter and dissociation. Once you determine the degree of counter and dissociation, suppose it is 0.2, that means it relays the unbound counter ions. So what would be the degree of counter and binding? 1 minus 0.2 is equal to 0.8. That means 0.8 means this degree of counter and binding is 80%, and degree of counter and dissociation is 20%. And method is that when you monitor the observed conductivity with respect to concentration means surfactant concentration. This is the CMC. So naturally this region is called the pre-micellar region. Pre-micellar region. And this is called the post-micellar region. So you simply determine the plot slope of this post-micellar region and pre-micellar region and divided the post-micellar region by the slope of the pre-micellar region and post-micellar, you will get the degree of counter ion. So it is also very short type of question. I have already told you that degree of dissociation for the micelles alpha and the degree of counter ion association is beta. This parameter reflects the ability of the counter ion binding on the micelles. And of course naturally the bigger the alpha, smaller the beta, and the ideal condition is that degree of counter ion binding should be more than 80%. That is the ideal conditions. Now in addition to that, whenever you study the surface tension with the help of this simple data, you can monitor one of the most important parameters, that is called the surface excess concentration. And what we do, we monitor the surface tension and we change the concentration. So we can plot a graph. This is actually not working. Okay, no problem. Change in surface tension with respect to concentration. So we plot a graph between surface tension and concentration. So from that slope value we can determine these things. And so this is a very important one of the properties of the surfactant, that what is the surface excess concentration. And if you determine the surface excess concentration, then you can also determine the minimum surface area. I think in M.Sc first semester you have determined these things. The area occupied per surfactant on the molecules, which is very important, a minimum. So for that we need the Avogadro number and the surface excess concentration. So these are also two important properties. There is a possibility of short answer question. Define the surface excess concentration as well as the minimum surface area. When I will teach the Gibbs adsorption isotherm, I will explain, I will derive this two formula. That is also related to this unit. But here I am just using that with the help of surface tension, how one can determine these two important parameters. And also, you can also calculate the surface pressure at the CMC. So it is also very simple, that one is the surface tension of the water and surface tension of the particular CMC, surface tension. Now, you must be surprised that you should know the actual size of the, basically if you see the literature, I have seen that it is just like your nanoparticle, 10 nanometer to 100 nanometer particles. But now with the help of dynamic laser scattering technique, DLS, and zeta sizer, one can calculate the actual size of that actual micelle diameter is also. I am taking from another research paper, the colloidal structural force at tool of particle correct and control dispersion stability. So they determine, there are a large number of research papers. So you can calculate the actual number of micelle diameter, 7.2. We also determine, but due to shortage of time, I am unable to prepare this transparency. So I have taken from a literature. So now I am coming the second part of this lecture, that is factors affecting the critical micelle concentration and micellar size. So first factor is the, again I am using my old research papers long back, I think 2008. It is 2023, 15 years ago, long back, we determined, one of my research scholars, Ashish Srivastava. He is now in MDC or whatever. So what we do, just why I am saying, telling all these things, because you will see the effect of the head group. CTAB is very common, C16, H33, NCH3B. And it is 1 millimole, 0.9 millimole, 0.8 millimole, like that. Now when I change the head group, cetyl triphenyl phosphonium bromide, or maybe here, because we have prepared different types of this phosphonium bromide surfactant. But here I mean to say, here is 0.1 is C16H33, C16H33. And here is also CPB. Again, it is another type of surfactant. That means if I change the head group, and there is a drastic change in, and it is again depends upon, tail is same, hydrophobic effect is same, but there must be some quaternary nitrogen and this triphenyl phosphonium. So there must be some specific effect. So where it is 1 millimole, and whereas in cetyl triphenyl phosphonium bromide is 0.1. So you see the drastic effect. And one of these possible explanation, I am not very sure about this explanation, but an increase in the hydrophilicity increases the CMC due to increased surfactant solubility in the aqueous medium and reduce the partitioning into the interface. That is also one of the reason for that. Because in cetyl triphenyl phosphonium bromide is a very big molecule, so its result is different. But in non-ionic surfactant also, the non-ionic surfactants have very lower hydrophilicity, and CMC values compared with ionic surfactant with similar hydrocarbon chain. Generally, it is a thumb rule that generally the CMC values of the non-ionic surfactants are less than or lower as compared to the cationic surfactant. Now here I am showing some of the very common CMC values of some anionic and cationic surfactant, anionic and non-ionic surfactant. You see, if is SDS, which is very common, sodium dodecyl sulfate is 80, of course 10 to the power minus 4, or 0.8 millimole, you can call it. Whereas Titan X is, where is 80, you see here 2.4. 2 in 20 is non-ionic 0.90. 2 in 80 is 0.10. So you can understand the, and always there must be some correlation between your experimental method, and whenever you do some experiment, you must compare with the literature value, because for the last 50 years people have been determining the CMC. So there may be different, in some cases exactly same, 1 and 1, in some cases 20.8, 25.0, like that. So you should not worry about these things. Now today I will give you that research paper of Professor Maulik. Now he has given a general picture of all these things. So this is some cationic. Here you see, as I told you, that CTAB is 0.8, DTAB is 16. Just then aggregation number you see here is almost 30 to 124. In some cases also, these are bile salt actually, sodium cholate and sodium deoxycholate is a bile salt, although it is a surfactant. Here is only 2. Can you imagine, only 2 and 4? Whereas in sodium dodecyl sulfate, which is very common surfactant, 50. You can ask me, sir, why people are not taking the C18 or like that? There is a problem of packing parameters and there is a problem of coiling and other things. So basically, people are using the most common SDS, most common CTAB, most common Triton X100, which is very important for analytical chemistry. And you see, its aggregation number is 134, and CMC is 0.03. That means very less amount of surfactant will be required to enhance the selectivity and sensitivity of the reactant. So people will always prefer such type of surfactant whose CMC is very low. Suppose the CMC is 65 millimole. So you need more and more amount of that surfactant. So it is not desirable. So that is the example of generation of new type of surfactant where the CMC value should be very low. So therefore, for analytical purposes, people are using the Triton X or Bridge 35 like that. This is also one research paper related to solution properties of, yes. Now after this head group, now we want to see the effect of tail group, that is the effect of hydrophobicity, like dodecyl, tetradecyl, hexadecyl, like that. So I am taking this from this research paper. See, this is very important. So you see that first is CTA again, which is common, that is 0.9. Just now there, if you look very carefully, there must be some correlation, because you know that C10, then C12, C14, C16. So we are just changing this tail group and changes, you see 65 millimole. So that means hydrophobicity plays a very significant role like that. Then 16, 3.7 and 0.9. Similarly, it is for the cationic surfactant. If I take the anionic surfactant like that, sodium dodecyl sulfate, you know, sodium dodecyl sulfate, C12, like that. It is CMC is 0.008 or 8.3 millimole, 8.3 millimole. Now I am taking the sodium tetradecyl, again 2.1. If I take sodium octyl, you see, that means when if we increase the chain length, CMC is decreased. That means if we increase the chain length, the hydrophobicity will be increased. That means the CMC is inversely proportional to the hydrophobicity. That means if I take C16, which is more hydrophobic than this dodecyl, more hydrophobic than the tetradecyl. So there must be some relationship between this chain length 8 or 10 or 12 or 14. So there must be some relationship. I am showing that graph with you. So, and increase in the hydrocarbon chain length, CMC decreases. First point. And increase in the hydrophobicity reduce the aqueous solubility. Naturally, C16 is less soluble, and increase in the hydrophobicity reduces the aqueous solubility of the surfactant and increase its partitioning into the micelles. Then micellar size increases with an increase in the alkyl chain length. owing to an increase in the volume occupied by Var surfactant in the micelles. So that is the reason for that. And there is a relationship. Again, it is an empirical relationship. Again, I am telling, there is no scientific reason for that. If you change the methylene group, CH2, CH2 like that. So it is an empirical relationship proposed by scientists that there is a relationship between log of CMC and number of carbon chains from 8, 9, 10, 11, 12, 13, 14. It is an empirical relationship based on large number of experiments. So, and the conclusion is that, I can show you the conclusion. Why we are getting a linear relationship between the log CMC and the number of carbon atoms. So log CMC is equal to A minus B and M. A, B are the constants. So as a general rule, it is a general rule that if I change CMC is half when the length of the state hydrocarbon chain is increased by one methylene group. As I told you that there is a relationship, but it is true only for ionic type of the surfactant. It is true only for ionic surfactant. For non-ionic surfactant, 1/3. That means for non-ionic surfactant, the addition of one methylene group, the CMC decreased to 1/3 of its original place. Again, I am saying it is an empirical relationship, but one must be know this relationship. Now, this is the effect of counter ions. Effect of, I have taken this, although this transparency is not very clear, but you can, if I take sodium dodecyl sulfate, it is 8.32. If I take lithium dodecyl sulfate, it is 8.96. If I take potassium dodecyl sulfate, it is 7.17. That means there must be some change, and it is related to this size, potassium ion, sodium ion, lithium ion, similarly this ion. That means counter ion also played a very significant role, and you can see this counter ions strongly influence the properties of the micelles. For example, size of the micelle formed with a cationic surfactant increases according to the series. You can take cetyl trimethyl ammonium chloride, cetyl trimethyl ammonium bromide, cetyl trimethyl ammonium iodide. Similarly, you have already seen. And the reason is that valency as well as the polarizability plays some role. Valency as well as the polarizability plays some role. A change in counter ion to one of the greater polarizability or valence leads to the decrease in the CMC. The size, electronegativity of the counter ion and the size of the hydration layer around the counter ion also play a significant role. And one of the reasons is that the weakly hydrated, highly electronegative ions are adsorbed more closely to the micellar surface and neutralize the charge on the surfactant more effectively. Now, last is, I think, effect of additives. Now, effect of additives is very simple. As I told you that micelle formation is driven by two effects. One is hydrophilic effect and the hydrophobic effect. So, if I add some electrolytes, so that will sit in between these two head groups. So, their repulsion will be less. So, naturally, the CMC will be decreased. Therefore, CMC decreased and aggregation number increased. Lowering of CMC of non-ionic surfactant also observed with the same thing. So, it is effect of additives. Last point is, I think, this is the effect of temperature. That again I am taking from a very good book, Surfactant System, Biology and Pharmacy by D. Atwood and Florence. So, there are two types of surfactant. One is, A is ionic surfactant and B is non-ionic surfactant. So up to certain level, you see CMC is decreased because sometimes when you increase the temperature, the water structure breaks. But in ionic type of the surfactant, up to 30 degree, suppose you perform some experiment at 20 degree, so it is gradually decreased. But when you again increase the temperature, so that is called the minima. That means there is no linear relationship between the CMC and the temperature. So, but there is exceptions is possible. So, what is my observation is that take home message that don't believe all such type of things, because it is better that CMC must be measured at various temperatures for a given system to be examined, and then of course you can predict, yes, for this, because there are a large number of surfactants. So it is better to perform the experiment and your result will tell you the actual nature. But it is a very general nature and very old. I am showing you the very old data. For non-ionic surfactant, the CMC decreases with increasing temperature due to increase in the hydrophobicity caused by the destructuring of hydrogen bonds between water molecules and this group. So therefore it is decreases. But for ionic surfactant, the CMC decreases to a minimum value and then increase. The decrease in CMC is due to dehydration. First part is same. But when we increase the temperature, so disruption of the structured water around the hydrophobic groups which oppose the micellization. So therefore again it is increases. So it is another property. Just quick I am going to this point. This is also very important for the student because it is called the Kraft temperature, or sometimes it is called the Kraft point. Kraft point means when you Kraft temperature is the temperature at which the solubility of the surfactant is equal to the critical micelle concentration. Suppose this is the solubility curve and this is the CMC. So when you increase the temperature, a particular point, when this value is equal to the CMC, that is called the Kraft temperature. It is solubility of the surfactant highly temperature dependent. Solubility is usually low at low temperature and gradually it is increasing, and because once this surfactant form the micelle, so after that point no micelle above the certain temperature because it is already been prepared. So the point where solubility curve meets the CMC, that is called the Kraft temperature. Now it is for the, of course, generally basically for the ionic type of the surfactant, and for the non-ionic type of the surfactant, sometimes what happens is we increase the temperature, so there is a phase transition and your surfactant solution becomes cloudy. So your surfactant solution becomes cloudy. So that is slightly different. So that is called the cloud point. So this is the last transparency. Of course, cloud points are characteristic properties of the non-ionic surfactant. The cloud point of a solution corresponds to the temperature at which dissolved solids are no longer completely soluble and participating in a second phase. That becomes the cloudy. When the temperature rises, the water molecules gradually break away from the ether bond, because most of the non-ionic surfactant are polyoxyethylene, like polyoxyethylene ether. So you can call it is a turbidity effect. The higher the cloud point, the wider the temperature range is used. So thank you. So let me summarize. Today I have discussed some of the important characteristic of the surfactant. I have given more trace on the critical micelle concentration and the factors affecting the critical micelle concentration. In addition to critical micelle concentration, I will give very elementary idea about the two other points. One is called the Krupp point or Krupp temperature, and another is the cloud point. In my next class, I will discuss them. That is, here there is no derivation, so therefore I have not used the board. But in the next class, I will derive the third part of this micelle, that is called the thermodynamics of the micellization. So I will discuss phase separation model and mass action model. So that is complete derivations. Okay. Thank you very much.